Hi, Akash. Welcome to the HealthTech Narrative Podcast. Thank you for joining us. Where are you speaking to us from today?
Hi Divyam. Firstly, thanks for calling me. And I'm currently working in Miami, the Sunshine State of US. It's no, it's already starting to get hot in here, and yeah, can't complain.
Amazing, amazing. Akash, you're here because you've done some really groundbreaking work in the field of AI in healthcare, specifically in relation to explainable AI or XAI, a concept where the AI is giving a working or an explanation as to why it comes to a particular output. I think the need, not just in healthcare, for something like this is very apparent because a lot of AI models work in a black box or a glass box sort of setting, and having an explanation component to why they come to a certain decision is key for building trust and transparency. But we'll get to that in a bit.
Sure.
How I found out about your work was your PhD paper that you had written. Your paper research led to the development of a prototypical model for classifying high risk atypical breast lesions. Can you share with us the challenges that pathologists faced that you identified in diagnosing certain breast cancer types and why achieving a consistent, accurate diagnosis is crucial in patient care?
Absolutely, Divyam. I think you have like got the right tone to ask this question. That what is the underlying difficulty that the pathologist face, while looking at the breast lesion. So we think of a cancer as binary, like most of the crowd, like either you have cancer or you don't have cancer. But there is a huge spectrum to it, wherein there are multiple subtypes within the pre-invasive part of breast cancer, which is quite complicated to look at, understand, and diagnose. So there is this gray area wherein, let me give you a quick example, right? So which when you look at a kitchen, you can quickly call the room as a kitchen. Like why? Because you see like a refrigerator, a gas stove, microwave, and all that. Like if I remove refrigerator from the room, or maybe even remove gas stove, would you still call it a kitchen? Probably, because you still have the microwave, you might have some cutlery here and there. But say I introduce like a working table in the same room, then there starts a confusion. I might call it a kitchen because I was trained on that data set. I know this place really well. But you come in and you tell, no, I like to have a microwave in my office because I like to heat my food and things like that. So you come up with a justification to it not being a kitchen, but like a working room, right? So similarly, in the pre-invasive part of breast cancer, there is this lot of amorphous nature and confusion, wherein there are so many features together, but there is no distinct marker that if I have this, like say X feature, I need to call it class A, or if I have Y feature, I need to call it class B. It is more like probabilistic. Like sure, like X percentage of this feature plus Y percentage of this feature makes me feel that I can call it class A with a certain confidence. So there are no like clear guidelines and specific rules which says when do we diagnose a certain breast lesion as the category A versus category B. So this is like the underlying uh, reason to why misdiagnosis happens, and why is there a high rate of discordance or disagreement between the
Hmm.
clinicians. It's true not just for breast lesion but other lesions as well. So
Got it. Got it. So
yeah.
the challenge is that there is no uniformity amongst pathologists or clinicians when they are trying to arrive at a diagnosis of a certain type of breast cancer, in terms of what constitutes the features of that particular
Absolutely.
type of breast cancer. Um, and you'd think that there would be methods, but I mean, there would be methods to come to a certain kind of diagnosis, but
Yeah.
what could you like maybe walk us through briefly as to why you think this non-uniformity sort of exists, and are there any
Sure.
practices or a lack of technology or something like that that has led to it?
Yeah. So if you take breast cancer, for example, so there is this book called as the World Health Organization Classification of Tumors. And so this is like a guidebook for most of the clinicians worldwide. And you can see that there are like, more than 10, 20 to 25 different subtypes within the breast category itself. So all of these subcategories are, most of it are in the pre-invasive state. So I would call something pre-invasive, where the cancer has not metastasized or become invasive, because an invasive cancer is comparatively easier to tell. When you look at the tissue image, the entire breast duct has exploded, and the cancer cells have populated in the neighboring regions as well. So it has metastasized, and but
Yes, yes.
but then I think the majority of the population, when they go for screening, they will some of them will be put under pre-invasive category, where the cancer has not metastasized, but there might be a tumor lump, wherein it could be gone if you have a surgery, right? Or they will tell you like, okay, this might become cancerous in 7 years down the line, 10 years down the line. So there is not like one or two subtypes in the pre-invasive category, but it's more like 20 to 25. But the problem lies in the space that if you group these subtypes together, they have different treatment options. And that's where the problem occurs. Because if you put the patient under, say, subtype 3 instead of 2, then the treatment for that might be more aggressive. So from the patient perspective, it's important for them to get the right diagnosis. But from a clinician's perspective, they take some time out to diagnose which subtype it is, and they usually give the worst diagnosis possible. What I mean by that is, even if they feel like 70% confident that it's subtype 2, but if they feel that they're 30% confident of subtype 3, they do not want to take a risk of under diagnosing the patient. So, they go towards subtype 3. And now, to answer your question as to are there any rules around this and where is the technology right now, it's very hard to quantify, because here we're talking at cells at a microscopic level. And unless we do like sufficient studies and as to tell where the demarcation lies, here we're talking about like microscopic level tissues, wherein, say, out of like 10,000 cells, 5 cells might be atypical. But then there hasn't been studies so far which says that, okay, like quantification of such atypical features will lead to cancer in the future. And it's very difficult to do, because so much of changes happen like on a regular basis, like within the tissue, within the cell. So there hasn't been studies so far to clearly say that if this is the atypicalness that I'm seeing within the tissue, and there is no way you can see what happened like outside this tissue section. Like, you are limited to the knowledge only there, like locally. And so there is a lot of like amorphousness or gray level to see, okay, this is the data that I have, this is what I'm going to look at. And here you're talking about an image which is of a size like 5 to 10 gigabytes, which is like there are like a million pixels in that image. If it's digitized, if it's not, under the microscope, the pathologists like zoom in, zoom out, pan in, pan out, and all of that. There's a high tendency that so they usually scan the slides in a raster scan fashion, but there's a very high tendency they might miss on some feature. They might miss something which could have put the diagnosis on a very different scale. Yeah, like
Got it.
like like for
Got it.
like for example, like in the kitchen, say there was this
Hmm.
printer at the corner, like unless you pay sufficient attention to that particular space, you would still think it's a kitchen. But then if
Hmm.
somebody like if there is an AI which picked that feature up and brought it at the surface, hey, look, you need to look at the printer, then you might start
Hmm.
thinking, oh wow, okay, then I really can't call it a kitchen. I think I need to tend towards being it a workspace or an office. So
Hmm. Got it. I'm loving
yeah,
the analogies you're giving.
yeah,
It's making me understand. And I'm sure it'll help a lot of listeners understand this. I have read your paper, and it's
sure.
definitely more complicated than that, but the essence of it is captured very well by you. Moving on to the model that you developed itself. Now, the PS series models you developed have shown to outperform the baseline models, which came before your paper, in
Yeah,
recall rates for
yes,
high. high risk breast lesions. What
Mhm.
this means is that your models miss fewer actual cases. Considering that this type of model that you built can be called an unsupervised machine learning type model,
Mm.
what were some of the critical steps and considerations in your model preparation that helped achieve these results?
Okay, so going to the technical aspect of it, so we formed what is called as a prototype set, which was separate from the training and the test data set. So we formed this prototype set to capture the diversity of the pre-invasive breast lesions that a pathologist
Mhm.
typically would encounter. Like, for
Okay.
example, again, going back to the kitchen analogy, like in the prototype set, I had one image where there was refrigerator, microwave, cutlery, and all that. But
Mhm.
there was another image where there was no refrigerator, but just the cutlery and microwave and all that. So all permutations and combinations. And then I created like a bunch of images like that for kitchen, which now forms my prototypical set.
Mhm.
Now it captures all the diversity of what a kitchen might look like. So what motivated us to do that is because we as humans, whenever we look at an object, we try to form associations. So similarly, I think in our case, the motivation was when the pathologist looks at an image, they form these mental associations with the images that they might have looked at, and what is the strength of those associations to call it a specific object. So that is the high level overview of the entire machine learning framework that we try to learn. So we formulated the objective function around that. So when you look at a piece of an image, how close is it to this prototypical set that we have formed, which captures the diversity of all the pre-invasive subtypes, and
Mhm.
how do you rank these similarities to the training data set? So this is like, I wouldn't call it as unsupervised, because the prototypical set was unsupervised, but not the machine learning framework, because now I let the machine tell me that, given a new image, I want you to compare this new image to all the prototypical images, tend to find your similarity as to, the features within your training image, how similar it is to the prototypical set, and then you have the label, so you learn the weights. Now you
Mhm.
will tell me that how much importance should I give to a printer in the kitchen versus a printer somewhere else. Like, how, so you will give me the weights, and you will tell me as a machine learning framework, that what is the weight of a refrigerator in a kitchen to call the image as a kitchen. The
Mhm.
weight might be high. What is the weight for a spoon in the kitchen? It might be very low, because you find a spoon in the kitchen, in maybe in the bedroom, or everywhere. So that's where the machine learning component comes in, because now it is
Mhm.
trained on a data set, and the data will tell me what weights or importances should I give. Now I take those weights and importances and I go to a doctor, and then I ask him, who's an expert, like, my framework gave me a very high importance for this feature to diagnose this cancer. Do you agree with that? If he says
Mhm.
yes, then we have an innovation, because now the machine learning framework has told me exactly what a clinician would think, how he or she would think,
Mhm.
right?
Mhm.
But if he has a contradicting opinion, like, then we revisit the framework and try to better it, because that's how it was explainable. There was always this communication between AI or machine learning with the pathologist.
So
Yeah,
let's just move to the heart of our discussion.
sure.
Um, on explainable AI. So XAI is pivotal in building trust within clinical decision making tools.
Right.
When I read your paper, you used these mathematical equations that read as gibberish to me, but which provided a comparison between seen and unseen images. You
True.
used statistical modeling, which turned qualitative assessments like this looks like a crib reform pattern into a quantitative measurement stating that this measurement is indicative of a crib reform pattern. You
Exactly.
used likelihood scores and heat map visualizations. Could you explain how these components of your model incorporate explainability and trust?
Sure. So coming to that, so crib reform is a feature which the pathologists use and know. So I think the first stage is detecting this feature correctly, because if you don't do that, then you can't incorporate that into the model. So we took care of that early on, and made sure that we had a very solid foundation to detect the cribriform feature. It's such a vital feature in detecting atypical ductal hyperplasia, which is something which is like non-typical, and it's quite concerning. So cribriform is like a refrigerator in the kitchen again, you cannot miss that. And it is something which will it by itself lead you to make decisions. Not always, again, but most of the time. So explainability here came in wherein we identified this feature, and this was part of the prototypical set as well. And given like new images, we again detected cribriform in all the images. Some images had, some images didn't have, and then trying to form association as to, okay, I have this cribriform feature. Compare yourself to the prototypical set, and let the machine learning tell me as to what is the importance of having this cribriform feature to being of certain category. And surprisingly or not surprisingly, the framework that we developed, it gave a very high importance to cribriform feature. And then when we took it to the pathologist, that's indeed that resonates or is in line with their medical training, because this is one feature that they shouldn't miss at all. And so that's where the explainability comes in. Explainability does not come wherein you already have a model and you try to fit in into the knowledge. It's like there's already a knowledge that is well established in the medical community. Does your AI follow that? Because, for example, if I have to have an alternate hypothesis here, if my algorithm detected cribriform and it said cribriform is not at all important in detecting
Hmm.
a certain category of pre-invasive breast cancer, then it's not explainable. I think it's it is in the opposite direction of explainability. It is like contradicting the hypothesis, which has been well established, that this feature is indeed helpful.
Essentially, what you have described so far is that the machine learning model can detect a cribriform pattern, which is usually, maybe not always, but usually a precursor to a diagnosis of a certain type of breast cancer. Now, the machine learning model has done this without understanding what pattern it should look for. It's just figured that pattern out, right? Based on the pre training data that it was given.
Mhm.
Now, once it's figured that pattern out, that was the purpose. It solved its purpose. It solved, the purpose of the machine learning model. What I loved about your paper was the explainability aspect of it, the explanation given that this is what it actually means, and it's telling the clinician that this cribriform pattern has sort of come out
Mhm.
of the exercise. Um, but it's not just telling it that, right? Like that would be the machine learning model doing its machine learning job.
True.
It's not actually explaining why it came into um, why it came to this decision. So could you explain, again, for the lack of a better word, could you rather elucidate why this explanation is important, how you incorporated this explanation into your model,
Sure.
and what this explanation looks like to a clinician or a pathologist?
Oh yeah, absolutely. I think the first thing is that the we try to formulate the explanation which the clinician would typically do mentally when they're looking at the image, on a day-to-day scale. So we try to understand as to when a pathologist looks at an image, very simple, they will look at some features. Some features will overpower other features, and then they make a diagnosis. So it is like the conglomeration of all these features put together, and every feature has a different contribution score to come to a final diagnosis. Some features are more important than others. Some features are completely exclusive, and it is if you it's like if this feature is present, then you don't look at any other feature. It's like, there are these overpowering features as well. So we tend to follow that in our framework as well, where we wanted to find those features which the pathologists typically pay attention to, and I would call it as like a bag of features. And it could, like, so I had, like, for example, like I have like 10 features. Then I let the machine learning framework tell me the contribution power of each feature, bring it all together, and come to a diagnosis. So here the explanation part of the framework is, like, if I have to tell it in simple words from a machine learning perspective, like, I diagnosed this image as this category because I detected X feature with a 60% contribution power, and I detected Y feature with a 30% contribution power, and I detected another feature with, say, like 10% contribution power, and I put it all together and put threshold on that, and that is why I came to this diagnosis. So this is the explanation part from the ML perspective. Now, from a clinician's perspective, when they look at this framework, I would call it as not a black box, like a white box. Why? Because I tell the clinician as to what features it is detecting and what is the contribution power. Now the clinician can tell, no, not at all, I would like to 60% is a very misleading contribution power of this feature, because I have like 30 years of experience in pathology. Like, I know what it is. I have seen like lakhs of images. I think it should be no more than 5%. Then we go back and introspect as to what happened. Why did it give this particular percentage? Was it lack of training data set, lack of the diversity of the data set, or we did not sample the prototype data set quite well, things like that. So we did all that, and now given any image, it detects all these features, gives it a contribution score, and gives it diagnosis. Now it's from the clinician can use it not just for diagnosis. He or she could use it just to detect these features, or he could come in and given his own contribution score to each of these features. Because I think one thing which the clinicians are hesitant right now is let AI take over the entire diagnosis of the tissues. So and we do not want to do that. So we are in a stage right now wherein I would say, like, we are building Tesla for pathologists. Right? Because at the end of the day, we are the driver. We take the car to a specific point, we park it, all of that. But Tesla car just gives you so many tools for you to avoid accidents. So we are trying to build AI to avoid any like misdiagnosis, speed up the efficiency, and just as a assistive or guiding tool. But so
Given your current position as a professional in this space, I think you are very well placed to answer this question. So,
sure.
my question essentially is, how does the output of your explainable AI models or XAI models generally, particularly features like heat map visualization, present itself in the real world to clinicians or pathologists? How does it aid them in understanding the AI's diagnostic process? Because then, when you take a model into the real world, uh, this the baking in of trust into the model is would have been done ideally by then.
Oh yeah, so that's a very good point that you brought up as to so just to reframe your question is, I have certain output, I would call it as output styles, and heat map is one of that. And how would that translate to making the model itself trustworthy from a clinician's perspective? So to answer that question, yes, there is this heat map visualization which you can see, wherein certain regions within the image uh, might be more susceptible for whatever you're trying to predict versus the rest. So it's all about the probabilities. So a heat map is generated by the prediction probabilities. Lesser the probability, it gets a certain color, mostly towards blue, and higher the probability, it's mostly towards red. So that's the blue to red spectrum that you have. So depending on whatever problem you are trying to solve. So here with the breast cancer, I spoke about diagnosis being the final outcome. And so this diagnosis could be formulated as to if it's a heat map visualization, then which regions contributed for the final outcome or the final diagnosis. So it's more about there are so many like post hoc visualizations, or you deploy the model and then you try to have the heat maps of the weights and all that from a technical perspective. As long as it does not resonate with their clinicians, day-to-day practice, it cannot be called as explainable. Like I think it is very important to talk the language of the field you are in, even from an AI, from the heat map perspective, for it to imbibe like trust. Like for example, if you're developing an AI model for a Tesla car, and say the outcome of this AI model is it presses the brakes very hard, and now it does that because it sees certain objects, it calculates distance, and it thinks that you might dash into this object, and then it takes a call. Now from a model perspective, like it's explainable, right? Because if when the developers want to think about it, they they don't want to understand the heat maps or numbers as is, but it should translate to something which is domain specific. Like again, it's about I detected like a person walking or who was crossing the road at this speed, and like things like that. So I think you can imbibe trust only if you open up the language of that particular domain from the AI. So it's not just about the visualizations or the post hoc analysis, but it should translate to something logical within in any domain that you are in. So
Yeah, I mean, very interesting that you gave that example of Tesla, because I think the explanation also needs to go to the user who is driving or sitting in the Tesla, when they look at the
exactly.
camera and they look at these various lines and maps that are being drawn in terms of objects that are coming in the way. And but coming just maybe coming back a little bit, making it more macro. In your opinion, should explainability be a standard feature across all AI models in healthcare, or are there any circumstances where explainability might not be as critical?
Yeah. So that again, that's a very good point, and explainability is critical, and that is what people are expecting. And as you know, in US they are formulating AI regulations, and I think the top takeaway with the AI regulations is you need to understand your failure modes, and you need to be open and tell when the model is failing. Otherwise, you cannot form a company out of it. You should be able to tell when the model is failing, on what kinds of environment will the model work well, and things like that. So explainability is critical given any domain. But uh, if I had to pick like one direction where explainability might not be required is drug discovery. Why? Because there you might think that you are trying to pick a needle from a haystack, and your objective is just to pick a needle in the haystack, right? Because that means you want to find this compound, for example, for COVID, or I don't know, for any other like diseases. You want to find this drug compound which binds to this virus, and there you have your new medicine, right? There you don't care about explainability. It's about your only objective is there is a huge lump of haystack, you want to find the needle out of it. So that's your objective. It's like, and then you have like then you win big. So I would say like some aspects of drug discovery is where you simulate like lot and lot of samples, try to simulate so many drug compounds, see like how it reacts to this virus. And it's more about like I think companies like they simulate like more than a million permutation combinations. You need like heavy supercomputer to do that. But then at the end of the day, it's just like this one shape of that compound which will lead to getting maybe I don't know a vaccine for COVID, or like a medicine for new disease. I think that's like one of the directions where I feel explainability might not play a role. So.
I was a little surprised when you said that. Are you saying that incorporating XAI into something like drug discovery would make that whole process more cumbersome and it's pointless?
No, I think one thing is that again I always go with a problem first approach. and it's always problem first, AI next. And
Okay.
then, like for example, you are in a library surrounded by a million books, and the answer to your problem is hidden in one book, which is and you don't know where it is. And if you have an AI to find that book, all you care is, I need that book. It's okay if you will tell me or won't tell me as to what you did to find that book, or explain yourself to find that book. But if I get that book as fast as possible, I'm good. And that, because that was my problem, and you have a solution there. So no, but if the problem is changed to something like, I need that book for sure, that's my first priority, but I also need similar books. Can you do that as well? And there you might want some explainability. Why? Because then you want to understand as to what is it looking at when it's trying to find that book. So
That's really cool, Akash. A really cool way of explaining it. When is it needed and when is it not needed? It closes the loop of these series of questions. I want to ask for applications like yours, where and for the work that you do, which significantly impact patient outcomes. Does frequency of the explanations play a role into building trust into the ML system, or does it become a burden, or is it a good to have or not to have in terms of should it be optional?
yeah, so I have like two answers for that. One is my domain, and then one is it's a general domain, right? So for my domain, I think it is still a challenge for adoption of digitization of tissue slides. And on top of that, here we're talking about AI to take over some of the things which could help the pathologist. So yeah, for to understand the what trust they will have in the AI system, I think frequency matters a lot. Why? Because we are dealing with cases which is not an apple to apple comparison. Like, every patient is different, every tissue type might be different, and when you observe it at a microscopic scale. So it is good for the model to get exposed to a diverse set of data, and unless and until it has passed through I would say 99% of the diversity, the explanations will play a vital role. And to put things into the general perspective, I think, again, right, if it's a Tesla car, like,
Mhm.
when you are driving on a US road, it might be very different from driving on the Indian road, right? So the
Mhm.
AI model that has been developed within the Tesla app on the US might not have taken some factors or some parameters for the Indian environment. Now you could test it out only if you let this machine run on the Indian roads, and then based on what we learned, you come back and you revise the model to But up until any field for that matter, unless you have not parsed the diversity of data set for that particular field, I think the explanations is always required to come in the to come to the front face to who the decision maker is. Like in the Tesla, it's me as a driver, so I'm the decision maker. And up until I feel confident. Yes, I will have the knob with me to turn the explanation on or off, but I need that knob to be under my control and not the corporation's control,
Mm.
for me to get trust into the system.
Understood. Understood. If AI systems are to be used by more people, uh, you've already alluded to this, but relevant people must be part of the design from the start, and different people need different kinds of explanations. In the experience that you've had, firstly, do you agree or disagree with the statement? I'd assume you agree. But
Absolutely.
secondly, how have you seen this play out in the work that you do?
No, I think so. I am a big advocate for involving the specialized people in developing AI, because again, you focus on the problem first, and here the problem is misdiagnosis. And who does that? Like, it is the pathologist, and they have some difficulty in diagnosing, because that's how, the data set is. So if you are trying to develop AI for them, you need to be in more or less constant communication with them, and you need to test out your algorithms, even your preliminary result, because early on you might be going in a very different direction, and it is good to fail, but fail fast, right? So you need to be in a constant communication with the domain experts in building your AI model. And again, because they will be the end users, and I would say like think global, but act very local. That you could think about building an AI system to do the diagnosis, but act local in the sense that, okay, which is that one thing that you would want to focus on, which might improve that person's efficiency by say 5% or 10%. So there we will see a win, not only in developing a robust and trustworthy AI, but also you could see a much faster adoption, because right now many sectors might be resilient no might resent adoption of AI into their workflows, right? But I think following this strategy will just help in better adoption, and help you make less mistakes when it comes to deploying this particular AI based strategy into your company.
On that note, I'd like to close this loop and get an end to the podcast. I want to extend a heartful thank you to you, Akash, for joining us all the way from Miami and sharing your groundbreaking work in computational pathology and the pivotal role of explainable AI in healthcare diagnostics. Your insights into making AI more transparent and understandable, especially in the critical field of histopathology, are invaluable to our listeners and the broader medical community. Thank you for being here.
No, it was a pleasure talking to you, Divya Mendel. Thank you for inviting and providing a platform to talk about it. And what you're doing is fabulous. And thank you once again for inviting.
Thank you so much.